Hi, my name is Scott Simpson, and today we'll be talking about Hückel theory. Hückel theory is an approximate method that's used to look at the electronic structure of molecules. Primarily, most of the time people look at pi systems when considering this. You sometimes talk about the Hückel rules in organic chemistry, and you in fact sometimes draw molecular orbitals based upon Hückel theory. It's sometimes also used in inorganic chemistry or organometallics, but this is the mathematical foundations behind this theory. So there are several approximations that are made when using Hückel theory. So all overlap integrals usually given the symbol S. We're going to use SAB. That's the overlap integral between orbitals on an S or on atom A and atom B are all set to 0. So all of those get set to 0. The next has to deal with the resonance integrals. All resonance integrals are set to be equal. In this case, we give them the symbol beta. Set. So they're all equal to one another. All resonance integrals between non-neighboring atoms is set to 0. So all resonance integrals of non-neighboring is set to 0. So beta is equal to 0 in that case. And then we also say all Coulomb integrals are set to alpha. Are set equal to alpha. Okay. And to kind of give you a reminder, alpha, again, we said that's the Coulomb integral. And that's the energy of occupation of an electron occupying that orbital. So, energy of electron occupying orbital. And beta, that's the resonance integral. And that has to deal with the overlap or the strength of the orbital interaction. So it's the overlap between those two. Okay, so these approximations, it's a simplified system, but they yield orbitals that can actually be pretty helpful in understanding the system. We're going to look at an example of this. We're going to look at an allylic radical. Basically, we have propylene, pulling one hydrogen off, leaving it as a radical. So we're going to investigate this system, which I'll draw in a moment. Basically, we're going to look at that guy. So we're going to consider the pi orbitals of a linear combination of carbon pz orbitals, one sticking out of space by the way that we drawn this. So the two pz orbitals in a propylene allyl radical. So we can count, we're only considering the pi orbitals. In this case, there are 3 pi orbitals. Let's write out our linear combination. So we're going to have some coefficient associated with that first orbital. We'll give that the symbol phi. We'll indicate what carbon it is. So this is carbon 1, that's carbon 2, this is carbon 3. So we'd say carbon 2 at 2pz plus C2 phi C2 2pz plus C3 phi C3 2pz. So that's what we're talking about. Okay. If we use the variational principle, we'll end up at the following secular determinant. So using the variational principle, we end up with H11 minus epsilon S11, H12 minus epsilon S12, H13 minus epsilon S13, H21 minus epsilon S21, H22 minus epsilon S22, H23 minus epsilon S23, H31, excuse me, 31 minus epsilon S31, H32 minus epsilon S32, H33 minus epsilon S33. So that's our secular determinant. That's all set to 0. Okay, so now let's make the Hückel approximation. So making Hückel or Huckel, some people say Huckel, Hückel approximation. When we do that, remember, non-neighboring terms are going to drop to 0. So, for instance, H13, 1 and 3, they're not near one another. So those terms are going to drop to 0. So we'll get 0 here, 0 here. Next, we said that all overlap integrals, we're going to set those equal to 1. Along in here. So these overlap integrals for these points are going to be set to 1. Any of them outside are going to be set to 0. The other thing that we have to keep in mind is that any of the indices that have the same, like H11, H22, H33, those are going to be our Coulomb integrals. So we get alpha minus E, alpha minus E, alpha minus E along the diagonal. Then any of these overlap integrals, or any of these integrals that are connected for atoms or orbitals close to one another, those are approximated to be beta. With beta, that resonance integral. Whoops, got to keep that in line. As such. And again, that's all equal to 0. Okay, we can make this a little bit simpler, so let's try to do that. So using some substitution and some simple tricks, we can make this a bit better. So if we take this and we divide by beta, that's going to make all of these beta terms 1. And it'll make our matrix look a little simpler. In that case, we get alpha over beta, 1, 0, 1, alpha minus epsilon, beta, 1, alpha minus epsilon over beta, 1, 0. So that's what our matrix looks like. So we divided by beta to get to this point. We can make this a little bit simpler. We can use a substitution. We can sub in x. So set x equal to alpha minus epsilon over beta. If we do that, our integral looks, or excuse me, our matrix looks even simpler. We arrive at this as our matrix. Now, all we have to do now is solve the secular determinant. We can do that using the rules of matrices. So if we do that, we get x, x1, 1x, like that, minus 1 times 1, 0, 1x, plus that last term is 0 multiplied through. We simplify this a little bit further. We get x minus x squared. Let's see. Should be minus 1, yep. Minus 1. Let's see. X gets applied through first term. Should be minus x. That we end up with, I believe. Yes. X is all equal to 0. Multiply that through. We get x squared minus x is equal to 0. Oh, x cubed, I'm sorry. So we get x cubed minus 2x is equal to 0. That's a simple equation that we can solve for. So let's do that. Let's pull an x out. Then we end up with x squared minus 2 is equal to 0. This we can factor. X minus square root of 2 times x plus square root of 2 is equal to 0. So now we have 3 roots. That's exactly how many that we should arrive at with our expression. We put in 3 atomic orbitals. We should get 3 molecular orbitals out, which we do. Now we can plug in for x. So let's do that. That first term, x is equal to 0. We have x minus 2 is equal to 0. And then we have x plus square root of 2 is equal to 0. So we said that x is equal to alpha minus epsilon over beta. Now we want to try and solve for epsilon. Those are the energies that we're looking for. In this case, when you manipulate everything through, epsilon 0, we get alpha is equal to epsilon. So the energy of that orbital is just equal to the Coulomb orbital. Or Coulomb integral, excuse me. And that next one, solve that in. Epsilon beta is equal to positive 2. Manipulate that through. Square root of 2 times beta. Manipulate through things through alpha minus square root of 2 times beta is equal to epsilon. If we do the same thing over here, in this case, negative square root of 2, negative square root of 2, beta, let's see, in this case, do this right. Should be a minus, but that moves over. This should be a plus, I'm sorry. In this case, 2 beta epsilon. That's what we should get. Okay, so now we get 3 energies out. That's good. What does this look like graphically? Well, we can represent this in an MO diagram, or a molecular orbital diagram that you've seen before. And if not, you'll see it right now. Basically what we do is we plot our energy along this axis. We get out 3 molecular orbitals, just like the rules you learn in general chemistry. That atomic orbitals that go in, the number of those has to result in the molecular orbitals that come out. So we can do that. In this case, we set the 0 of energy. That's our alpha. And we get alpha plus square root of 2 beta, alpha minus square root of 2 beta. If we're talking about our allylic radical, we said earlier that we have 3 pi electrons. So 3 pi electrons, that means we have to fill this with 3 electrons. 1, 2, 3. An interesting consequence is if you look, the energy between these 2 orbitals, the lowest energy orbital and the highest energy orbital, is equal compared to that 0 or that center, that alpha. However, if you go on to other theoretical methods, that's not always true. Usually that anti-bonding orbital, the one that's highest energy, tends to have a little bit more dispersion, it's called. Okay. What do these orbitals look like, though? So we're going to try to draw these. The first one is where all the p orbitals are in phase with one another. The second one, we introduce a single node. The node's going to actually cut in between that C2. And we get a phase change across those. The top one, though, is anti-bonding. It's got 2 nodes. And there you go. An interesting consequence is if this guy is going to react, it will most likely react on carbon 1 and carbon 3, just like you learn in organic chemistry. The reason is if you look at that orbital, it's singularly occupied. It wants to react to either take on an additional electron or give off an additional electron to result in a diamagnetic system, one where all the electrons are paired up. Okay. So we've gone through how to do Hückel calculation, a little bit about those energies, what each of these terms mean. If you have any questions, please feel free to email me or leave a comment below. Thank you very much.